Space weather has been with us for many years. It was first noticed back in the 1840s when telegraph systems were able to run without batteries whenever a solar flare occurred. They didn't quite understand that, but it was kind of fun to be able to talk to Boston without their batteries.
Their space weather is like weather on the ground, but up in space above 50 kilometers.
Space weather is the problems caused by flares on the sun, which emit soft X-rays and extreme ultraviolet light, and the particles that also come from the flares and the coronal mass ejection.
The sun emits light and particles all the time, but sometimes when we have a solar flare, it emits more light, especially in the extreme ultraviolet, or EUV. All of this light and particles travel towards the Earth and interact with the Earth's atmosphere. The EUV causes the Earth's atmosphere to warm up, and as it warms up, it expands. This causes drag on the satellites in low Earth orbit. The biggest effect of the drag is your GPS. If the satellites don't know where they are because they're at a lower orbit than they're supposed to be, your GPS is off. The ultraviolet light from the sun, some of it does make it through the Earth's atmosphere, and that's what causes sunburns.
For example, if you compare the energy, what energy is released during a mean solar flare, I can say that that amount is enough to supply United States in electricity for more than 150 years, just one solar flare.
The higher energy radiation is the energy, the radiation from the sun that actually is absorbed and modifies the constituents of Earth's atmosphere.
And since the sun varies a lot at these short wavelengths, the extreme ultraviolet, the upper atmosphere varies a lot.
It's kind of a wave, and as you know, waves can go really fast, or they can be very long and slow, and so there are different lengths between one hill and the next. It could be a little length, or it could be a big length between the one hill, like in the ocean. I would say UV's this.
We are very concerned about space weather, about influence from solar flares, from high solar activity to our life, to humans' life.
Just about everybody on Earth relies nowadays on the performance of satellites and space-based assets that we use. These satellites, their lifetime, their performance, what they can do and what they can't do, is limited by the local weather environment, and since they're in space, we call that space weather.
And there's many effects of space weather, such as when the sun increases, there's a storm, a flare on the sun. Those flares will heat up the thermosphere, the outer space part, that affects our satellites. So it affects our satellite drags, which can drag them back down lower. It can affect our communication because we use the thermosphere, ionosphere for communications. And it can also disrupt many services on the ground. Now, space weather has many aspects that might affect your personal life. One example might be you might be flying from here to Japan, and the normal flight is to go over the poles so that it's the shortest amount of time and the least amount of fuel and least cost to the airlines. But when there's a solar storm, space weather event, then they have to redirect the planes to not fly over the pole, but to go the long way around, which of course costs more for the industries.
The extreme ultraviolet is a wavelength range that is totally absorbed in the Earth's upper atmosphere.
And we have only opportunity to study solar flare in EUV when we have space projects, because EUV is not accessible from the ground.
You have to build and design an instrument that will work, survive, and make accurate measurements up in space.
Well, Solar Dynamics Observatory is being built as part of NASA's Living with a Star program. Living with a Star was designed to study space weather. SDO will be orbiting about 36,000 kilometers over the surface of the Earth.
So we put the instrument into orbit as opposed to taking ultraviolet radiation measurements from the ground, because the atmosphere acts as a filter. And the other reason is from our orbit, we can constantly look at the sun as opposed to having it stationary on Earth and not get readings during night.
EVE is a satellite instrument. EVE stands for EUV Variability Experiment, and it's designed to make measurements of the sun in the very shortest wavelengths called the extreme ultraviolet.
A project like EVE involves at least 35 people at LASP, spanning from research scientists with PhDs down to undergraduate students who do things like program or help the engineers or sit in the lab and take data. We are trying to establish how the sun varies, how it affects the Earth's atmosphere, and produce models of that variability of both the sun and the atmosphere in order to be able to predict what's going to happen in the future and to be able to tell what is happening right now.
The atmosphere density models say here's how dense the atmosphere is or how light it's going to be, and that then affects the amount of drag on all these debris objects and on the satellites that are operational. So the guys at NORAD can actually track all these objects, and they'll say, gee, we know that this object is going to go a little bit faster over the next few days because it's a less dense atmosphere, or we know it's going to be slower over the next few days because we have a big flare going on and the atmosphere is denser. And so we know where that object is going to be in its orbit, and thus we know whether or not it's going to hit the space station or not.
And SDO is really one of the first missions for NASA where the data is real time. So we'll be getting data down directly from the satellite to the ground, to our computers in less than a minute, and we'll be able to look at that data and make scientific decisions within 15 minutes of that.
So what I do is the data calibration, which is taking all of our data and making sure that the data we give the scientists in the community for climate models, for solar physics, is the best possible data that we can provide them.
Everything about EVE is gee whiz. We're building an instrument that will go into space. It will orbit the Earth at a geosynchronous orbit. It'll stare at the sun for 5 to 10 years, making measurements better than any other instrument has done in the past. And it will answer important science questions.
It's really fun being a scientist working on things going to space. You might say I'm a rocket scientist, but really it's just a lot of fun to watch an instrument coming together and going into space and making measurements and seeing the data products.
There are two kinds of science research projects. There are those that are basic science, humankind trying to understand how things work, and there are those that are more applied science.
Continue 0.1 miles, then turn left on Arapahoe Avenue.
The results of which help us in our everyday life. The EVE project is kind of one that spans both of those. We're doing basic science to understand how the sun varies, but we're also using that information to see how the solar variability affects Earth and human endeavors.